engines now building up to 7.7 million pounds of
All
thrust.
engines running. Launch commit. Have a liftoff.
We have a launch commit and we have a liftoff. The swing arm is moving back. We've cleared the tower.
Roger, clear the tower.
Houston is now controlling.
Roger, how does it look?
Throughout the ages, humans have been drawn to the mystery of Mars, fourth planet from the sun.
9 or 8.
Only recently, with the dawning of the new millennium, has the vision of landing human beings on the surface of the red planet transformed into an ever-nearing potential reality.
Contact light.
Come on out here and give me a salute. Big Navy salute. Off the ground, on the floor. There we go.
Magnificent sight out here. Magnificent desolation.
After the first steps on the moon in 1969, and later with the successful landing on Mars of huge unmanned Viking probes in 1976, many believe the next step in space would be the sending of humans on the Martian surface. But the U.S. space program became sidetracked with shuttle missions and the building of the International Space Station. Eventually, the public lost interest in Mars. However, when reports began surfacing in the late 1990s of possible life forms and meteorites originating from Mars, a renewed enthusiasm in the red planet was generated. Unfolded here are the latest mission outlines, ongoing research, and necessary technological developments required for the undertaking of the first manned mission to Mars. A Mars undertaking is a monumental task, so much so that some wonder why humanity should be concerned with a planet 200 million miles away from our own existence, investing enormous amounts of time, effort, and resources to get there. For others, however, a Mars mission is a necessary step in the continued search for life beyond Earth. Seeking out new life forms has such tremendous implications for the future of Earth that it is viewed as a priority for any upcoming Mars excursion.
We believe there was water on Mars at one point, and there may still be subsurface water on Mars today. We know with certainty, anywhere on life, that we find water, we find life. It may be a little amoeba, it may be a single cell of life, but we find life. And maybe we could find fossilized life on Mars. This would be an unbelievable breakthrough in human understanding, just to know that at some point in time, life might have existed, even at a very low form, in a place other than Earth.
Certainly one of the main themes has to be looking for clues as to the origin and evolution of life in the solar system. That is, looking for fossil evidence on Mars, or bringing pieces of Mars back so we can examine them here on Earth to look for fossil evidence of life that might have evolved on Mars. Looking up near the polar regions where there still is frozen water ice, which may mean that there's a possibility there might be some residue, a life residue from that earlier era.
Was there ever life on Mars? If there wasn't, why wasn't there? Because we know Mars was warm and wet at about the same time the Earth was first evolving life. Mars had conditions that could have evolved life as well. And if it did, that means that there are now many broader range of places, a much broader range of places where you can expect to look for life. Maybe we could look for red planets that are smaller and are farther from the sun than the Earth is, for example, and have a chance of there having been life evolve on a much broader range of conditions than just the Earth. So it has profound implications for life in the universe.
Many of the key meteorite samples containing what scientists believe is a life form presence were discovered over 100 years ago. Only recently were they determined to have come from Mars. Scientists theorize that a high-speed meteor impacting onto the Martian surface caused thousands of tons of soil and rock to be ejected from the planet. These ejected samples then spent perhaps millions of years in space before finally impacting at various sites here on Earth. In what many believe to be the single greatest discovery in Earth history, scientists from NASA and Stanford University revealed their conclusion that the meteorites contain the remains of Martian life forms. Analyzing a meteorite sample discovered in Antarctica in 1984, the scientists claim that certain structures found in the rock are actually fossils of single-celled organisms, similar to ancient life forms here on Earth. Organic molecules found in the rock are believed to be residue of these life forms. There are, however, many noted scientists that dispute these claims, strongly urging that further research be conducted regarding the search for life on Mars.
The Martian meteorites, they are igneous rocks. And also on Earth, there are no forms of life in igneous rocks. Where you find the ancient life on Earth are sedimentary rocks, which were once in form of individual minerals and only compacted later on by temperature and pressure. Those igneous rocks are the wrong samples to look for remnants of life.
If we had problems on the ground, we still had a second opportunity.
Currently, the debate continues to rage as to whether life existed or still exists on Mars.
One of the most compelling questions about Mars is, was there life, and searching for that life. But we don't really know what we're looking for. We can't even come up with a rigorous definition of life. In some sense, when people ask me, how are you going to search for life if you can't define it? The answer is, well, we'll know it when we see it.
The controversy over the possibility of life on Mars has served to generate extraordinary public interest in Mars exploration and space in general.
I've been talking about this subject for years. It's a great subject and it's a great story. You know, I mean, it's about time that Americans really started taking an interest in it. I think if we don't self-destruct, that we're going to go out there. You know, I mean, it's the nature of evolution to explore wherever you can. I mean, to where like every life form spreads its territory as far as it can. You know, and the human race is the first earthly life form that's been able to go anywhere else.
Sending human beings to the Martian surface is perhaps the only way to firmly resolve the issue of the existence of life on Mars.
What's really saying is that you're relying on sort of the holistic, intuitive approach to exploration that humans can bring. You don't have a well-defined task that you can program into a computer and say, make this measurement, take this analysis, and then tell me what you find. It's a much more interactive process, searching for life, searching for fossils. And certainly right now, we only know how to do that with human beings.
You know, a common question in the space program is always the tension between, do you need people or should you just use robots? People are adaptive. When something happens, they're able to react like robots can't. They have versatility and flexibility and manual dexterity. So there are things that people could do that robots can't. But we will not send people until it's economical and the potential for scientific or economic benefit is high enough. And that's the approach we're using. Yes, we need people. Yes, we need robots.
A technologically advanced armada of robotic rovers has been developed for eventual deployment on Mars. These rovers will act as scouts for the human mission to follow.
You can imagine if you want to explore another planet like Mars, that you need to get down to the surface of Mars in more than one or two spots. You can't imagine understanding the Earth from having landed on the Earth in just one place. It's much too complex a planet. Mars is equally complex, and we need to find a way to systematically go back to Mars every opportunity there is with a series of small probes that can land on the surface, eventually drill down beneath the surface, looking for water, looking for any other evidence of the early era, left from the early era of Mars, when there was lots of water on its surface and where simple life forms could well have evolved.
I mean, we've obviously got a lot to do to get our act together here. You know, going out there might be one way to do it. You know, I mean, I don't see exploring space as ignoring earthly problems so much as it's a different way to grow. You know, we have to grow our way out of our problems. And that's a very serious way to grow. You know, you learn a lot doing it. You learn a lot about yourself doing it. You learn a lot about the planet you just left. you know, and I think that's important. It can all be useful to the growing experience of the human race.
When you send a human being to, say, Mars, we would like those human beings to do the most important things they can do during their stay on Mars. That we will know because the robots will have explored Mars well enough that we know what the most important questions are that the astronauts can help us answer, and we will know where the most important places are for those astronauts to visit. So the robotic program will lay the groundwork in terms of understanding the Mars so that we can be most effective in our initial brief human explorations of that nearby planet.
The manned Mars mission will be an international rather than a nationalistic undertaking, unlike the American Apollo space program of the 1960s and 70s. Still, the mission will not be cheap, simple, or totally without risk. The technological requirements alone are monumental.
Over the past 2 to 2.5 years, we conducted a study led from a group at the Johnson Space Center and other NASA centers to study a human exploration mission, a human exploration program. And we have just finished, and we are compiling that report now. But what it did is put together an end-to-end scenario for human exploration of Mars.
The problem with Mars is that most people don't understand how difficult it actually is. As far as they're concerned in a presentation, a TV documentary, or whatever, it is simply another planet, like the moon. What they don't really understand is, for example, if I'm the Earth and you sitting there on the other side of the TV screen are the moon, Mars is several hundred miles beyond you.
The most critical technology that has to be developed is low-cost, reliable Earth-to-orbit access. We need a new rocket. Right now it costs $10,000 a pound to take material into low Earth orbit, and then from low Earth orbit we could transfer to Mars. For 6 missions to Mars, that would have cost $100 billion. That's unacceptable. This is the major barrier to getting to Mars.
Many scientists and engineers believe that current interplanetary rocket propulsion technology and fuel systems will be unworkable for such a large-scale Mars mission. The next generation of propulsion systems will likely involve ion or fusion reactors utilizing the light element helium-3 as primary fuel. Presently, helium-3 is being tested in laboratory fusion reactors on very small scales for eventual use in small, unmanned spacecraft propulsion systems. Eventually, this technology will be expanded and utilized in large-scale rocket boosters capable of matching the power output of current chemical propulsion systems. Helium-3 was first considered as a fuel source for interplanetary spacecraft when it was found in massive quantities and readily available on the Moon. This determination was the result of analysis of the moon rocks brought back by the Apollo astronauts. Corporate studies are currently underway to investigate the likelihood of establishing a helium-3 mining colony on the Moon. Development of this technology will also have important applications for society at large, possibly replacing fission nuclear reactors as a source of electrical energy in the 21st century.
One of the long-term benefits of a helium-3 based energy economy, and lunar helium-3 in particular, is that it enables a whole bunch of other things to happen. It enables us to bridge our way to Mars because the launch vehicles and the technology needed to settle the Moon and to extract helium-3 are essentially the same types of technologies necessary to go to Mars.
We are privatizing the space station. privatizing the space shuttle and using those resources to fund the first human missions to Mars. That is our goal, to see that happen. That way everybody gets what they want. The government gets its big showcase mission to Mars, people who are into Mars get that. Those of us who want to start businesses in the Earth and the Moon system get a chance to do that. It all works together in a wonderful synergy, because if you can use the inspiration of Mars to excite the public, then space in general and space activities in general will rise.
Harnessing helium-3 as an energy source not only clears the way for Mars travel, but is an important step in colonizing the Moon as well.
The primary byproduct of producing helium-3 on the Moon is hydrogen. And in the course of extracting the helium-3 and hydrogen, you also produce water. Anywhere you produce helium-3 on the Moon through heating up the soil to extract this solar wind gas, you are going to produce hydrogen and water. And those are the essential components for self-sufficiency on the Moon. And indeed may well be the source of fuel and oxygen and water for space travelers to Mars and for the early settlements on Mars.
This same technology could be utilized to produce fuel on the Martian surface. As a result, fuel for the return trip to Earth would not have to be stowed as payload on the initial flight to Mars.
This subject of extracting rocket propellant from the Mars atmosphere for the return rocket to Earth, it will save enormous amounts of money if we can produce propellant on Mars. It can save effectively half of the mass that you have to launch from Earth to Mars, which means that in general, that would save about half of the cost of the mission if you didn't have it.
The atmosphere on Mars, however thin, still has carbon dioxide. We can convert that carbon dioxide with a little added hydrogen into methane fuel and oxygen for breathing gases. Perhaps there's water on Mars. We could convert that into a very high energy fuel, hydrogen and oxygen, and we could also have water to drink. We could have oxygen to breathe.
For several years, we argued, a group of us argued that closed life support systems, that included plants, closed ecological life support systems, would be essential to long-term exploration of Mars or the Moon. And we tried to get people in NASA interested on the engineering side to incorporate those kinds of approaches into the mission design.
We need to take seeds with us and not foodstuffs, because foodstuffs are very heavy. So we'd like to be able to learn how to plant foodstuffs on Mars in the Martian soil, in the Martian environment. And then we'd like to figure out how to have what's called a regenerative life support system, so that we could recycle the air we breathe and we could recycle the water we drink, so we don't have to constantly take, so we don't have to take a lot more with us. If we could overcome these issues, we're on our way to Mars.
Given the cost of such a venture, it is unlikely that any single nation will assume the entire financial burden and develop all the required technologies. Likewise, the makeup of the crew will reflect the international character of the mission. Unlike the Apollo crews, which consisted solely of Caucasian American males, the Mars crew will no doubt comprise men and women from a variety of participating nations. The initial manned mission to Mars will involve a crew of 6 to 7 astronauts, 2 of whom will be pilots, with the remainder being engineers, geologists, and medical specialists. These astronauts will most likely undergo training at the International Space Station that is currently under construction, since the crew must adjust to living in space for 2 to 3 years at a time.
When we get to human missions, it's almost certain we're going to have an international endeavor, just like International Space Station Alpha. I mean, that's got Europeans, it's got Japanese, it's got Russians, it's got US, and I think that's the way we'll be going to Mars with people. So we're already international and getting more so.
The motivation for exploring Mars politically is cooperation, not competition. And cooperation by its nature is not a goal-oriented task, it's a process-oriented task. From a political point of view, what's important is not going to Mars and coming back, but the process of working together to go to Mars. So, in fact, the logic forces you the other way around. The best way to make Mars a beacon of international cooperation is to have the mission take as long as possible. Stretch it out. So I'm actually not optimistic that we're going to go to Mars and anywhere near the rush that we went to the moon.
I could foresee a day, perhaps 10 years from now, as early as 10 years from now, where we may want to decide there's a compelling reason to go to Mars because we got the mission cost down to an affordable level, and we see scientific benefit for early human exploration. And these explorations could take place within my working lifetime.
So to get ready for possible human expeditions to Mars, we need to find out where are the interesting places to land, where are the safe places to land, where is the resources so that we can start living off the land as soon as possible. And if we can do all that, by about 2018, we hope to be able to field a human mission to Mars. 2018 is a nice time frame because you've got the space station that's going to be operational in a few years. People need to live and work on the space station for a while to see how much zero gravity they can stand, and they need to be able to understand something about partial gravity. You know, Mars is 3/8 of the gravity of the Earth. So by 2018, we ought to have the technical infrastructure in place and a sufficient understanding of Mars so that we know how to send people there.
The most viable of all the launch systems proposed by NASA uses only slight modifications of current hardware involving a two-phase procedure. First, an unmanned booster rocket containing the propulsion system for the round-trip journey to Mars would be launched.
Mark 1 minute 12 seconds, coming up on period of maximum aerodynamic pressure on the vehicle. Mark 1 minute 41 seconds. Pass through max Q, still looking good. Through max Q, and everything looks good.
Shortly thereafter, the manned vehicle, housing the habitat module and crew, would also be launched. Once in low Earth orbit, the two spacecraft would rendezvous and dock together.
Ryan is hanging in there pretty well. She looks great.
The same to us.
Put out now, Houston.
Roger, looks like a real smooth join-up.
Okay, we're captured there, Houston.
Roger.
Houston, we're hard docked.
From there, the spacecraft would leave orbit on a trans-Martian trajectory.
Booster systems engineer reports ignition on the third stage. The thrust looks good, he says.
When we leave Earth orbit, it is very dangerous, and this radiation could be very serious for the astronauts, ultimately causing them cancer and could cause them to have very major health problems. We've got to figure out how to protect the astronauts against these cosmic rays. And we're working with new materials, we're working with screening procedures. We hope we'll be able to develop techniques for protecting the astronauts against radiation.
launch with just enough fuel to get you, say, to the vicinity of the moon, and then be met by a service vehicle, if you will, from the moon that would then resupply your hydrogen, your oxygen, and other materials that you need for the much longer trip to Mars. Yes, the moon can be thought of as a service station in space. You probably would not visit it on your way to Mars, but you would meet supply craft coming from the moon in order to add to your consumables or to what you need for life support, for fuel, for getting into Mars orbit, and so forth.
As you're getting 10,000 miles and 20,000 miles and 50,000 miles and 100,000 miles, and and everything you've ever known. You know, I mean, like the whole history of the human race is getting to the point where you can cover it up with your thumb. And that's a very powerful psychological force, you know, for all of those people.
Mars missions are constrained by the planets, by the relation in their orbits of Earth and Mars. You can only go and you can only come back at particular times. You're going for 2.5 or 3 years, and you have to take with you everything that you need, including all of the spare parts or the smarts to fix things that break. So in fact, once you commit to a Mars mission, you're going for 2.5 or 3 years, no matter how long you choose to stay on the surface of Mars.
Go for undocking. Okay, retro, go. Fido, go. Guide, go. Control, go. Telcom, go. GNC, go. Ecom, go. Surgeon, go. Capcom, we're go for undocking. Hello, Eagle, Houston, we're standing by, over.
As the spacecraft nears Mars, the landing vehicle would separate from the return module, which would remain in Martian orbit.
Eagle, Houston, we see you on the steerable, over.
Roger, Eagle, contact. Good radar data. We're now in the approach phase. Everything looking good. Altitude 4,200.
Houston, you're a go for landing, over.
Unique to the Mars mission is the fact that the
Roger,
landing
understand. Go
craft
for
will
landing.
enter the
3,000
atmosphere
feet.
without assistance from the Earth-based mission
10 and 50
control.
feet down at 4.
This is due to the 15-minute
Altitude,
communications
velocity
delay caused by the 200 million
down.
mile distance
20 feet.
between planets.
11 forward, coming down nicely, 200 feet.
Landing in
4.5
this manner
down.
makes the
5.5
maneuver
down.
exceedingly more difficult than the
100
mission-control-assisted
feet,
moon
3.5
landing
down.
of Apollo 11.
Altitude, velocity,
As a
light.
result, success
3.5
or
down.
failure would
20
depend
feet.
entirely on the skill of the crew and
11
the
forward,
spacecraft's
coming down
computers.
Nicely, 200 feet. 4.5 down. 5.5 down. 100 feet, 3.5 down. 9 forward. Okay, 75 feet. Car's looking good. Down a half.
From the knowledge gained during the robotic excursions, the landing site for the Mars mission will be determined based on the location most
40 feet down,
hospitable for
2.5.
human beings.
Picking up some dust. Straight shadow. 4 forward, drifting to the right a little. 30 seconds. Forward. Contact light. Okay, engine stop. We copy you down, Eagle.
When humans go to Mars, they're definitely going to be stepping into a hostile world. And it's interesting because the reason that they're going is because at one time we think Mars was very much like Earth and has degenerated to the cold world we see today. And they will have to, the humans that go will have to bring a little bubble of Earth with them in this to survive on Mars.
They will land on the surface and inhabit a set of facilities that for the most part have been put down before they were actually launched from Earth. So you would send the habitats out, you would send the rovers out, you would send the equipment for producing propellant for the return out before the crew ever left, deliver it automatically, robotically, have it set up and waiting for the crew to get there. So the crew would come out in their habitat, go down to the surface, have this set of chambers and rovers and suits and such waiting for them.
There's been thoughts about whether we should have a national mission to Mars to plant the American flag, or whether we should do it cooperatively with other nations. It'll be very appropriate to work together because science is the domain of the human species. It'll also be an opportunity to cooperate and perhaps not have a variety of flags being planted all over Mars and starting the process all over again where we had war on Earth.
As far as what actual astronauts on the surface are going to be doing, I would expect them to be working their way out in concentric circles or spiral or whatever, wider and wider, farther and further away from the base, looking for signs of life at first, looking for different and very interesting geology, those types of things.
You're unprepared for visually what everything looks like. I mean, like, there's no sense of scale or distance, you know? I mean, like, even out in the desert, you know, you see a telephone pole a half a mile away, you know? I mean, to where, like, that telephone pole cues you what your distances are. You know, there is no way to tell how far away anything is, you know, to where, like, the angles, you know, I mean, like, the horizon is much closer. So it's a hard place to find your way around, I would think, you know. I can imagine getting lost.
Another important consideration in determining a landing site is based on where the crew would most likely find life forms, if they indeed existed, or still exist, on Mars.
Geologists, and particularly planetologists, for many, many years have felt very strongly that Mars had a more Earth-like environment in its early history, and that if life was forming on Earth 3.5 to 4 billion years ago, then almost certainly the same processes were occurring on Mars, and that we ought to see evidence of that when we get there.
It would be somewhat surprising if one would have had on Mars similar conditions as we had on Earth, say 4 billion years ago, and life would not have developed there. I would say, and I am convinced, that if there was life once on Mars, it was life with the same kind of mechanism as life produces itself and replicates itself on the Earth.
Mars and Earth were similar enough in their early history, we think, that it's likely that if life evolved on Mars, it's probably going to be similar in some broad context to life on Earth. If we were searching for life on Pluto or somewhere completely different than the Earth, then of course we could not expect it to be Earth-like. But Mars is similar enough that it's probably going to have, in broad brush, the same kind of systems that we have. And that's good, because it means that we have a chance of being able to recognize it when we see it. So I think the secret to searching for evidence of life on Mars is to go to ancient lake beds, go to places that are now dry, but at one time had a lake, and to dig down through the sediments in the bottom of those lake beds and look for evidence of organisms that would have lived in that lake.
Our lander is going to be landing in the ancient terrain of Mars, hopefully near an ancient lake bed. So we'll be able to see if there was ever, maybe be able to see if there was ever life on Mars, see if we can find some indications of, you know, if you find fossil scum around the edge of the lake bed, you know there was life there. Maybe we probably won't find that, but maybe we can find some indications.
Is there now life on Mars? We don't know. There certainly are potential niches, ecological niches, where life might have evolved as very simple forms of life, might have evolved in order to survive to the present day. We just don't know, and that's one of the things that's going to be exciting about the investigations of Mars.
The thin Martian atmosphere allows that the solar radiation, the solar UV, penetrates towards the surface, and in this way sterilizes everything, kills any possible forms of life. There has been the suggestion that life might have retreated towards certain niches at depths, and so this cannot definitely not be absolutely excluded.
The surface of Mars today is much too dry and much too cold for life. The only possibility that we can see now that there might still be life on Mars is if it's living underground in some sort of chamber that's being heated by a volcanic source with ice melting into water and sort of an underground stew that could maintain life. It's possible. We have no evidence that it's there. That'll be something we'll be looking for, but we don't have any direct evidence that it's there yet.
They might go hundreds or thousands of kilometers over a couple of week period to study the rocks and to take samples and bring them back, and they'd be able to do some of the analysis on those samples right there on the surface. So if they found something really interesting, they could maybe go back out and look a little bit more to find out what was going on.
Given the availability of resources on the planet, the planned establishment of at least a semi-permanent base on Mars is also being researched. An important mission goal will be to assess the possibility of maintaining a long-term human presence on the planet.
One of the slogans my organization created in reaction to the Apollo program was "No more flags and footprints." The idea that you would have one or two missions or a series of missions that would be dead ends on Mars is unacceptable to us. In fact, we will fight that politically and in the media. We believe in permanence and settlement. We believe in an orientation. Even if you can't sustain the first two missions, at least you create the infrastructure that can be used later on by those who follow. That's a frontier approach as opposed to a nationalistic, program-oriented approach as we had with Apollo, and we have to do that on Mars.
They'll also look at what the resources are that can be utilized. At some point, they will actually start drilling into the surface and seeing whether they can extract water from the subsurface, look for evidence of liquid water down below the permafrost, perhaps drill holes down and try to tap into a water supply, or utilize other ways to extract water from the environment to support the outpost. They'll learn eventually how to make bricks and how to refine the dust to make iron and metals and such. The materials should be there. And so you can imagine that in time, you could derive everything that you needed for living there on the surface from the surface materials.
We know there's water because we can see the polar caps. And the water, in fact, when Viking did an analysis, they found that the dirt was full of water. In fact, it was so full of water it saturated their instruments, so we don't know how much water there is. But water has been somehow absorbed into the soil. And so there's water, there's oxygen can be made out of the carbon dioxide in the atmosphere. Oxygen can be gotten out of the rocks because we know they're iron oxide. And so you've got power and oxygen and water and dirt. What else do you need?
What we would do for a while is take little factories that we build on Earth and set them up there with their power supplies and let them produce. At least in the beginning and early stages, it's just a few people, so you don't need a lot of factories to do that. In fact, the plant that is necessary to produce the propellant to send a crew of 6 back from Mars is probably not much bigger than an ordinary office desk.
At the conclusion of their stay, 6 months to a year after arriving, the crew would leave all of the facilities intact, so that following missions may also make use of the settlement.
Okay, it sounds good. We think so too.
Heavily laden with rock and soil samples, as well as fuel processed on the Martian surface, oxygen extracted from the thin carbon dioxide atmosphere, and foodstuffs grown in the Martian soil, the crew would prepare to take their leave of Mars.
Director Gene Kranz now taking a status check with his team. Go, no go for ascent. Standing by. Ryan, you're go for liftoff.
Capcom, Ecom, Surgeon, GNC. Guidance, you happy? Go. Fido. Go. Capcom, we're go for liftoff.
Houston, you're cleared for takeoff. Roger, understand. We're number 1 on the runway. Work stage, engine arm ascent. Beautiful. Very smooth. Very quiet ride. Here you go, Houston. Going right down the track. Everything's great.
Once in orbit, the launch vehicle would perform the delicate task of a rendezvous and docking with the orbiter. This maneuver would likewise be conducted without any assistance whatsoever from mission control. After nearly 2 years into this mission, the crew would then have to settle in for the year-long journey home. Some scientists believe that the astronauts and Martian rock samples should be delivered to a laboratory on board the International Space Station for a long quarantine prior to returning to Earth. Once the safety of the crew and the safe handling of the cargo is assured, both would then be transferred for the flight back to Earth.
When we bring samples back from Mars, we want to be very careful and cautious to make sure that there's nothing in that sample that could be a danger to the biosphere, not just to humans, but to anything. We all seen examples where organisms introduced into a new place where they've never been before have wreaked havoc on the ecosystems there. So for that reason, the current plan is that when a sample is brought back to Mars, we treat it as if it's full of pathogenic, dangerous microorganisms. We treat it like it's a jar of Ebola or something, and until we can demonstrate to ourselves that it's safe, we hold it in a facility like you would if you were dealing with a very dangerous microorganism on Earth.
Upon their safe arrival on Earth, these astronauts are likely to receive the biggest hero's welcome since the return of the Apollo 11 moon mission in 1969, when Neil Armstrong and Buzz Aldrin placed the first human footprints on the lunar surface. The full extent of future implications for life on Earth as a result of the Mars mission cannot yet be determined. Should life forms be found in Mars rock samples, further expeditions and additional searches for life elsewhere in the universe are sure to follow. Such a momentous discovery will certainly afford humankind reason for reflection on our own existence and place in the universe. Like the Apollo program that spearheaded the American technological boom of the 1970s and 80s, the technological benefits to humanity as a result of explorations on Mars are limitless.
If we can learn to live on Mars, or even to visit Mars, we can learn to live in other places. But we're not going to learn to live in any place else in the solar system until we've learned to live on Mars. Mars is not much harder to get to than the moon, fuel-wise. It just takes longer. And Mars has all kinds of resources that the Moon doesn't have. So Mars is just a lot friendlier place to visit than any place else in the solar system. So I think it's inevitable that's where we're going to go.
The United States is a spacefaring nation. The purpose of an agency like NASA and a laboratory like JPL is to essentially expand that frontier of human activity, to constantly move out, to do things no one else has done so that human activity can gradually expand into the full realm of space. That is, I think, a very important part of the future of this nation.
In the next 500 years, if we don't destroy ourselves, who knows where we'll go? You know, I mean, there's a whole universe out there waiting for us. You know, I mean, I think that, to me, validates the adventure or the journey and understanding of who we are and our role in the universe. I mean, like, what does this beautiful blue-green globe have to do with all the rest of it? That's real meaningful to me.
Right now, we're sending robots to Mars. But why are we sending robots to Mars? In my mind, we're sending robots to Mars as scouts. They're going to check it out so that can be followed by humans. Why are humans going to Mars? Humans are going to Mars to see if it could be a long-term home for life. We're also scouts. We're scouts for the broader phenomenon called life. And ultimately, that will lead possibly to terraforming Mars and putting a biosphere there. And it's important, I think, to think of these as a continuum. Think of them as steps along the way, and the ultimate goal, at least in my mind, is another planet that has life.
We now can talk seriously about the settlement of the Moon, where settlements are self-sufficient, and the settlement of Mars, where those settlements are self-sufficient. And indeed, at least the Moon and Mars provide an option for the human species to establish new ecological enclaves elsewhere away from our Earth. The resources almost certainly are there for self-sufficiency. So Mars settlements will indeed be able to take care of themselves over the long haul. But to get things started, the Moon again is the bridge, and the keystone to that bridge is helium-3. That seems to me to be a very important philosophical goal for the human species, as well as one which is extremely exciting to many, many young people.
There's a lot of water that has to pass under the bridge. There's no need to make decisions now, but there's certainly a need to dream and think of possibilities. And that's what we're all about at NASA. We're about dreams and visions. And while we undertake a logical sequence to get towards these dreams, we bring back economic benefits and intellectual benefits to make our life richer on Earth. It's not spending money in space, it's enriching life on Earth, and that's what we're all about.